Okay. Okay, so the standard averages, so this is the Metropolis-Hastings pseudo-marginal delayed acceptance type algorithm. And so I'm going to, so without loss of, well, basically the essential idea is conveyed by the Metropolis-Hastings algorithm. And so this is as follows. So at iteration k, so everyone here knows this. So we do as follows. We sample from a proposal, and then we accept, so with probability so I'm going to our target probability is going to be designated by nu. So in the IS algorithm, so in IS correction, so this is where if we have, so we have this is the algorithm at each iteration, and then after we run that for m times, so we form the estimator. So let's call this direct. I'll just call this direct method, or actually I'll just say Metropolis-Hastings. So then we can estimate using our standard average. In the IS approach, then, so IS correction. So we have a measure, so mu, with support of mu containing the support of nu, and so now we can run, for example, the Metropolis-Hastings. So x and as before, so with probability so with this probability, we accept. And then we run this algorithm, and there's a phase 2 afterwards. So then there's a phase 2. So we set so Wi, and so often you only have basically the unnormalized version. So I might also use Wi. So this is equal to nu, some unnormalized version, and then we form the estimator. So an estimator like or if it's a self-normalizing estimator. And so these are the two basic approaches: a direct method and an important sampling method, where we use an approximation. And this DA, so delayed acceptance, so I've heard multiple times. So this, so you're well aware, you can also use an approximation, but it's still a sequential algorithm, and that you have to run in iterations. and you evaluate often the expensive nu. So with this IS correction, you draw first, you can first run an approximate Markov chain targeting mu, which can be much cheaper, and then you can use, you can form the weights in parallel. So if let's consider then, if we look at the running time then of this approach, so let's put here. So this is the running time. This is the clock time basically. And if we put here the iteration of the algorithm, so iteration, okay. So, and this is for the, let's look at the metropolis, so the direct method. So basically we have to evaluate this nu at every iteration. So it's going to look, so when we evaluate, it's going to, the clock time basically goes like this. And if we do the same thing though, and now we look at the IS correction. And let's say that we have H processors. We have some number of processors. So here in the first phase of the IS, we only have to evaluate mu, which is only a fraction of the cost. So we'll be doing something like this. And this is at iteration n, so now we're done. And then once we have all our, we've drawn then all our x values, then we can do the parallel sampling. And so instead of having to do this staircase, we can run in parallel, and so it will look something like this. And of course, if you have multiple processors, you can already do the IS correction down here because you only need one processor to run the sequential bit, and you can start generating the weights as you go. And so then this would be even shorter. But you can see the idea is that we want to be able to use the parallel ability instead of waiting. So in this direct approach, you have to wait to evaluate the nu before you can go to the next iteration. Here, you don't need to evaluate the nu. You only have to do those at the end once you've run your whole chain. So this is kind of the idea of why, in practice, the algorithm had a better computational efficiency. This is parallelability, but now I would like to talk about the asymptotic variance. So if we don't even look at this issue of using the parallel bit, so if we just look at the statistical efficiency, what can we say? Are there any guarantees? And so this will be the subject of this talk. And please interrupt if something is unclear or you'd like me to go at a different pace or mention something. But so I'm going to kind of, for those, I'm sure you're all aware, but I'm going to introduce the idea of asymptotic variance, and then we're going to look at comparison methods and try to compare these two approaches. So the asymptotic variance so if we have a chain and I'm going to speak here about reversible chains, and it has stationary measure mu. And if we look at a stationary version, then we define the asymptotic variance for an L2 function. So as limit of this, so it's this variance, and I'm going to look at mean zero, so f bar is equal to f minus is mean. Yes, sorry. So this is this, and let's see if we can kind of expand this. And now if we use that, we are using a stationary version of the chain. So we can write this so I'm going to only look at values of j less than I. And then I'm going to basically bring everything over here. And so since we have to subtract off the diagonal. So when I equals j, that's the only term that I need to subtract off. And now if we look at this sum, basically, so if here is I and here is j, we want I to be less than j. And so we're interested in summing over this. So we can write this and so we have I. And how much is this? So this is n minus I, or so we can write this as 2. And maybe if it's clear, I can use a different letter here. K sub L. And so this is a sum over n, and then we divide by n, so I can already subtract this off. And so now we can see that this term, so we have basically, we have the lim and so sorry. So this is F2, and we have this sum here 1 to n. Sorry, this is 0. So, and of then K sub L. And we have this minus F. And then we have a minus the lim as n goes to infinity of 1 over n. And so minus 2 and the sum of I of L equals 0 to n of F. And so there's a fact from real analysis that so if AK, so if this is finite, then this implies that the lim as n goes to infinity of K AK equals 0. So this term here will actually go. This will actually go to 0. So if we assume that this sum over all, so over autocorrelations is 0. So if this is finite, which is equivalent of saying that the asymptotic variance is finite. So and so now we're left with this. So you can see that it's so formally. So this is formally. This is then 2 times F if this inverse would exist. So this inverse, if that exists, basically when K has a right spectral gap or is geometrically ergodic, so you can use this representation. So it doesn't. We can't assume that in general. So we're going to play around just a bit. So let's look at, with lambda, some real number between 0 and 1. So lambda k is a subprobability kernel. So this is less than equal to 1. And so, but we can't, how can we relate basically something like this to asymptotic variance? And because here we have clearly, we have a Markov operator and there's no direct way, so, but there's actually an indirect way. So there's a result that goes back to Bellman. And this is, so 1968. So let's let, so A is a self-adjoint operator. And we're going to assume that it's invertible and positive definite, so F for all elements of the Hilbert space H. So then we have a characterization for its inverse. in terms of this supremum and this supremum is actually, and the supremum is attained. So at G defined to be A inverse F. So this is a very abstract result. So the title of this paper was something about some characterizations of inverses of matrices, and it was then the first time it was kind of modernly discovered to be useful in the Monte Carlo context was in the 90s. So there's some physicists, Caricciolo, Pellicetto, Sokol. So they have some paper about some non-local Monte Carlo method, and they dug up this result and they applied it, and it's been also applied by Christophe Andreu, Antonetta Mirag, Geyer, Matti Viola. So lots of people have used this result in various papers since, and so the proof is actually very simple. So this is from Andrew Viola, a paper on the establishing some order. So we just use the positive definiteness. So this is, we know that this has to be, so A inverse So this has to be, because this is, so A is positive definite, so we can write this out as then and then we have so then we have this plus G. And these terms, the cross terms, so we actually end up with just minus 2, and we have the F. Yes, so it's this FG. And then if we bring things to other sides, so this implies that A inverse is also self-adjoint. It's easy to see. This is then greater than or equal to 2 FG minus GAG. And then so it's greater than equal, and it's actually the equality is attained so with the G star. So that's the proof. Yeah, so I've written here positive definite. Yes. So that's, yes. If you want, it's positive semi-definite. So I assume that it has an, yeah. Yes. So now so now we have this subprobability kernel, lambda k. So by basically, if you look at its Neumann series, so you know that it has an inverse. And so then we can write a formula using this equation. So then we obtain basically, so we define basically this. So the definition, so asymptotic variance a sub probability. And so this is going to be then defined to be so it's going to be then 2 times the supremum of over all G L2 mu of 2 times F and so minus G. So, and then we subtract off, as always, this squared. So this is from, so if you look at this formula, right, this is what we want. And now can we relate these two operators? And so if we write now, so let's write, if we write basically the 2 F, so I'm going to first write, so G, F. So I can write this as F. This is one thing. So this is then, it's the identity plus lambda k times 1 minus lambda k inverse F, of course. And so now if we look at this formula, especially when G is attained, we have that so var lambda k lk f. So this is then, so it's 2 and so now we can combine these terms. So I'm going to write, so it's 2 minus 1 minus lambda lambda k times 1 minus lambda k inverse. So I've just combined everything. So this is then equal to f of 1 plus lambda k minus lambda k. And now we can apply the spectral theorem for self-adjoint operators. and we can write this then as a measure over its spectral measure. So this integral over its spectral measure of 1 plus lambda alpha over 1 minus lambda alpha. And and now we're interested, of course, as lambda goes to 1. So this actually, so as lambda goes to 1, so this converges uniformly to and this is exactly the asymptotic variance of our original operator, Markov operator, KF. So this is how we can relate the two asymptotic variances. And we only need to look at this perturbed subprobability, so this subprobability kernel, and how it acts, and then we can take the limit. So the proof now is quite simple, actually. So we were interested in comparing these direct methods with the importance sampling. So we have a theorem. So this is with my advisor, Matti Viola. So we have two kernels, two chains with invariant measures mu and nu. And so as usual, we have the support contains the support of nu. And I'm going to assume, so F is always is L2 mu. And we have these conditions. So I'm going to define this right here to be, this is going to be defined to be, it's called the Dirichlet form, so for the subprobability kernel. And with lambda equals 1, it's the normal Dirichlet form. So we have the condition that, so psi of lambda g is less than or equal to some constant c times Dirichlet form of the K chain. And we have that, so W, so this is the weight. And this is going to be, so W of x is uniformly bounded by C. So everything can be written as random Nicodemus derivatives, but for simplicity, I'll write it like this. And so these are the two conditions. And you'll notice that does this look familiar? Does this look similar to any other comparison result that you know? So everyone knows, and it's so the Peskin ordering or the Peskin tyranny ordering, and that's when basically if we only look at if we only look at A, and so if I'll write this down here, but so if we only look at A and we assume that mu is equal to nu, and we have that C is equal to 1, then we obtain the very popular Peskin tyranny ordering. So this is a strict generalization. So, I guess I haven't said the statement So then we'd have that the variance of k. And so this is actually the variance of the importance sampling correction. It's easy to show. I'll show later if we have time. Plus so this is less than or equal to the variance of the direct chain plus, so modulo a perturbation of mass, basically these two measures, we have so to speak a quasi-ordering, so an ordering up to a perturbation, multiplicative and additive constant. So you can see that. So we know, so it's easy to give examples that either can do better, and so this actually shows that this relates that fact that either can do better because you have this perturbation factor and you only know it up to a constant c, but at least you have this result. And so the remark, so mu equals nu c equals 1 only a. So this is the Peskin-Tierney ordering. And okay. Yes, it's the same C. And so this is a uniform bound on the weight. And so you don't get anything by having different C's, basically. So for simplicity, I just have the same C. And in the proof, basically, this simplifies. If you have different C's, you have a slightly more involved formula. It doesn't really tell you much, so I just have the same C here. So now the proof is very simple. Let's see how we're doing for time. Okay, wow, time went. So I don't think so. The proof is in the paper, and I think since I only have 5 minutes. Okay, 10 minutes. So I might get back to the proof, but I think I'd like to mention. So this is the marginal case. So this is where we've looked at x. X is just one space. So if we have time, but now let's consider if we have so we were interested in the kind of model where you have x equal to some kind of product space. So your model parameters, for example, and you have some latent variables or nuisance parameters, and and then so we run basically we're going to run this kind of marginal chain, theta k, and then we are going to form the importance sampling correction based on estimators over this latent space. So often the model parameter space, so dim of t is much less than dim of the latent variable space. And so we're actually most interested in comparing the chains where in this setting. So there's another result of this. So now I'm going to write, so W of star of theta is defined to be mu, so nu star of theta over mu star of theta, where so nu star is just the marginal. And so now I can write, so this version, so this version that actually has the most kind of power is that we only need these conditions. So before we had, so this is for all G element of L2 mu. And now I'm going to change this. So I only need knowledge of the marginal version. So I can add the star here. And then we're going to have somewhat a small perturbation. So at the cost of doing this, I have to add some things. So and yes. So then I have to add so there's an extra weight factor, and okay, so f squared. So I believe, and so I can write just to make this clear. So this is this C is usually might be very close to 1. And I can just and so instead of looking over this huge joint space, I only have to consider basically only the marginal version. Yes. And so if we look at, so if we have a good approximation, so basically often this C is quite equal to 1. So if you use the first version, so the black version, then C might be very large. You might have unbounded weights if you look on the extended space. But if you're only interested in the marginal version, then if you have a good approximation, so if this is going to be the mu star, and then so the true often, so that maybe this might be the new star, and you can see that if you look at the supremum of the weight, it can be very close to 1, and it's so this is the amazing thing about the importance sampling correction is that if you look at the augmentation basically of the kernel in the measure, you have a forgetfulness property, and so you can marginalize out the latent states very easily, and so the proof follows very similarly. So I think I've run out of time, so I think I'll open up the floor for questions. Yes.
I can't really remember. From memory, there was you could come up with a simplified model for the state space model. So that would sort of simplify. That would give you your mu, I guess.
Yeah, that's so. The amazing thing is, so how you use the pseudo? You mean like the pseudo margin? If you in the pseudo marginal setting? Yeah. So everything basically simplifies down, so it can be written in this framework, and it's more involved. Yes.
But in that case, it's so easy to bound that W star is my question.
Right.
That's in the space, right?
Yes. So it's a theoretical result. But what do you mean by the bound?
I mean, like if in your application, is it
Yeah.
to explicitly compute that bound, for instance?
So basically it comes down. So the W star, if we can write nu as if this is some prior, if this is proportion to a prior times the likelihood, and then we have. So I'm going, if I only look at basically this measure here, so this is going to be proportional to that, and then the mu, this is going to be proportional to this. So let's call this the approximate.
So the L star is induced by a simplified model when you integrate out the different variables.
Right. So basically, you're looking at something. This is the ratio of the likelihoods up to a factor, a constant.
Seems a bit tricky, I guess.
Right, right. In practice, yeah, but theoretically, it's just to give some kind of idea about the two approaches, and so yes.